Can you see my slides now through the Zoom link? Let's see. So why don't we put in the chat what the... Actually, why don't you put in the chat what the live stream link is for people who are online? Does this sound good? And then I think I'm just going to get started. Can you hear me through the microphone? Can people at the back hear me? Let's just start with people in the room. Okay, I'm going to try to talk loud. You can hear me? And then we're going to check if people online can hear me once they connect. Let's see. Okay, so I think you're sharing now. Is that right? Okay, so I don't know if that's a good idea. So should you be sharing or should I be sharing here? I think I should be sharing. And then I think you just have to figure out what to put on the live stream. See what we've got here. Okay, welcome everybody. Sorry for the setup. Should be smoother in the future. The idea is I like to use a mix of Zoom or slides and the Blackboard, and Zoom isn't high enough resolution. So we're going to live stream things for people who can't make it in and record everything and put it on the website afterwards. So hopefully you'll get value for the few minutes that you spent watching us do this. So welcome to ECE 1756. If you haven't already, maybe in the break or right after class today, just go fill out the short survey. It's going to take you, 3-4 minutes. It gives me some idea of what the background of the class is, and then I'll share it with you so you can learn a little bit about your classmates. So let me give a quick overview of what this course is about. So the details are in the syllabus on Quarkus. I'm just basically going to summarize what's in there, because many of you may not like reading syllabi. And I should say, so welcome back in person. Hopefully you're happy to be back in person. Hopefully we stay in person for the whole year. We'll see how it goes. So what are we going to talk about in this course? It's basically two related but somewhat different topics. So the first one is how to use FPGAs. So what are they? Why do they exist? What are their strengths and weaknesses? And we're going to start talking about some of that today, and then we'll go over it for the next few lectures. Basically, programming models. You're going to see that FPGAs are extremely flexible. You can make them do kind of anything, which means that you have such freedom. You need to think about how you're going to organize your computation. And a way to do that is to think about what are called programming models. Ways to structure a computation. So we'll talk about some common programming models that you can use to kind of organize how you get things done in hardware in general, but in FPGAs in particular. And that kind of goes hand in hand with optimization techniques. Some programming models are more efficient than other ones. And we'll talk, as part of doing that, we'll talk about the strengths and weaknesses of FPGAs versus other compute devices, because you shouldn't use an FPGA for everything. So they're good at lots of stuff, but there are other things that other devices are better at. So we'll talk about some of those contrasts. And then that'll take somewhat less than half of the course. The larger, maybe 2/3 of the course is, okay, hopefully at this point you're convinced that FPGAs are useful. You know how to use them effectively. How do you make a better one? So if you were an FPGA architect working for Intel or AMD, or Microchip, how do you create good components of an FPGA? So there are function blocks inside them, things called logic blocks, RAM blocks, DSP blocks. There's this programmable interconnect that ties everything together. How do you make that efficient? And then what are some alternative architectures or recent enhancements that people have looked at? So putting registers right in the programmable interconnect, incorporated networks on chips, and so on. This isn't a major part of the course, but as we talk about this, sometimes we'll talk about CAD tools, because you can't use FPGAs without advanced CAD tools. So we're going to talk about, well, what can the CAD tools do and not do very well, because that's part of deciding what makes a good FPGA. If a CAD tool can't use it well, then it's not very useful. And it's also part of doing your designs efficiently. If you, let's see if this actually will write or not. Maybe not today. If you can't get the CAD tools to implement your design efficiently, then it's not a great style of design either. Okay, so that's kind of the overview of the topics. I'm sure nobody care as much about grades in this course, but just in case you're a bit curious, you might wonder, well, how am I going to be evaluated? Not a major concern, but I'm just a little curious. There'll be 4 assignments that are worth 65% of your mark. So the first and second are basically hardware description language optimization on current FPGA. So you're implementing designs on a current FPGA and you're trying to optimize them. So this links to those programming models that I talked about. There are different ways you could structure those computations. We're going to ask you to structure them in a few different ways and see how efficient you can make them and which of these programming models seems to be more and less efficient. You also do a little bit of comparison to, how well would a CPU or a GPU do on some of those computations too, so you get a sense of, is this kind of computation a good match? So you'll write some hardware description language. You're not writing enormous amounts of, normally people write it in System Verilog. That's the hardware description language that's kind of most widespread at U of T, and that we write, kind of the test bench and infrastructure you go into, so it's the easiest one to use. You don't need to be a super expert in System Verilog. System Verilog is just the next generation of Verilog, so if you know Verilog, you basically know most of System Verilog. We'll teach you a few of the nice features that you should use and forget some of the more hacky pieces of Verilog. You don't need to be a super coder in HDL, because you're not writing enormous amounts of HDL in this course. If you don't know any HDL, you will have a little bit of catch-up to do. And I'll post a few resources on style guides and so on for writing hardware description languages. Okay, that's the first couple of assignments. So how do you use a current FPGA to make a computation efficient? The third one's a little different. You're going to write a CAD tool that basically it's a particular kind of CAD tool. It figures out how to use the RAM inside of an FPGA efficiently. And you're going to use that both as an exercise in how do you write CAD tools, because you can't use this kind of chip without advanced CAD tools. And you're also going to use that tool to investigate how can you make the RAM architecture in these chips efficient. So you can do what-if analysis using the CAD tool that you write and say what's a good idea and what's a bad idea in terms of how you would build the RAM blocks inside of an FPGA. And then the fourth assignment is also doing FPGA architecture experiments, looking at what makes more or less efficient programmable routing, but in that case you'll use a pre-existing open source CAD tool called VTR, so you'll be kind of writing scripts and running it, but that CAD tool is too complicated for you to write from scratch, so you'll run one. So kind of diverse assignments. 10% of your mark's going to come from weekly readings, so every week I'm going to assign 1 or 2 background papers that I think are interesting and relevant to what we're going to talk about, and put up a little questionnaire, 4 questions or so about the paper that will take you maybe a page to answer those 4 questions. They're each worth 1% of your mark. We'll actually assign about 20 papers. So if you read them all, do all the questionnaires, that's great, and I'll take the best 10 questionnaires that you send in. So you'll probably get 10 out of 10, and if you actually read them all and write a questionnaire on them all, I'll probably take that into consideration at the end of the course that you did an exceptional job on that. So if you're kind of close to a break point in grade, I'll take that into consideration. And then the last thing you do is a research survey paper, which is worth 25% of your mark. So you'll summarize about 10 papers that are related to the course. We'll talk about this later on. You could pick there's all sorts of different subtopics you could choose. Best practice in this is you kind of survey the landscape, so pick maybe 10 papers and cite them and say what they're doing. And then pick 2 to 4 that you think are particularly interesting or show contrasting approaches and dive into them in more depth. And I want to get your insights, your thoughts. So not just here are 10 abstracts that I read, kind of reproduced one after the other, but how do these fit together? What do you think maybe some of these papers got right? What do you think they might be missing? And it's 3,000 words or less. And there's no final exam. So I don't know if people like final exams or not, but there isn't one. So you can tell me in the course surveys at the end if you really wanted an exam. Okay, so all the assignments are individual. So, you learn from each other. So general discussion with other students is fine. I'm totally confused. What is this prof writes these super confusing assignments? Has anybody figured out what the heck this means? That's all fine. I don't understand why I get this weird error in my HDL. Can somebody tell me? That's all fine. But basically, if you weren't comfortable posting it on the course discussion board, like you're asking such detailed questions of, can you show me the code for this? Then you shouldn't ask that to somebody individually either. So if in doubt, is this too much collaboration or not, ask me. You're going to submit all your assignments through Quarkus. They're all run through an automatic plagiarism checker. Basically everything at U of T is. Don't copy text verbatim from papers. So if you take more than a few words of text without rephrasing it from a paper, it's considered plagiarism. You don't want to do that. So rewrite it in your own words. If you need help, post on Piazza. So there's a link on Quarkus to the Piazza discussion board, and I put all your email addresses in it, so you should all already be enrolled in that. In general, when you post on Piazza, if you have a question, often a lot of other people will too. So by default, just post publicly. Let everybody see it. Maybe another student will answer or benefit from the discussion. If you're putting part of your solution in, you're like, here's my answer to assignment 1, but I've got this problem. It doesn't work in this part. Okay, that you should make a private post. So don't post your solutions. And then only myself and Amin. Amin is the course TA. Amin, you want to put your hand up so people can identify you. He's our videographer and course TA. Then we'll only see it if it's private. I also have office hours on Zoom every Thursday from noon to 1. So just drop in if you have a question. If you're lonely, if you think I'm lonely, right? Whatever, you kind of, I don't know, I'm a little worried about Professor Betts. He seemed a little needy last week. I'm going to dial in and have a virtual coffee with him. All very appreciated. You can email myself or Amin. You can ask me after class. You can ask to schedule a Zoom meeting. So if you're stuck on something, speak up. Lots of ways to ask and get information. Okay, so we're doing the lectures in a hybrid format. So it's mostly in person. I think most people are showing up in person, which is great. But we're going to record and post all the lectures as well, just because there may be people who can't make it for a variety of reasons. I know some people can't, like there are even like visa issues getting across the border right now. So to try to include everybody, we're going to live stream the lectures. I mean, how is the live streaming going this week? Is it looking good? Actually, for people who are on Zoom, let me quickly check the chat here. Let's see. So for people who are on Zoom, were you able to find the live stream, and is everything working okay? Okay, so there's a few of you. So anybody on Zoom, is live stream okay? See how this is going. Okay, well, maybe not. Okay, yes, okay, that's great. So it is actually pretty complicated to set up. I think Amin has been installing software and doing background research on how to make all this stuff work for the last several days. So thanks, Amin. Okay, so we'll start at 4:10. We'll end at 6:30, or hopefully some weeks a little bit earlier. We'll take a break in the middle. I'll post the slides so you can download them off Quarkus in advance, and scans of any handwritten notes. I kind of like to write on the blackboard for some things too. There are no direct participation marks, but I appreciate participation. And if you participate, and I remember that, I kind of take it into account as a tiebreaker. If you're kind of near the edge of a grade that I go, well, this person was a great participant, I'm just going to round it up. Okay? Let's see. And I think that is it for kind of course overview. Any questions on that? Is it all pretty clear? The assignment late policy is in the syllabus as well. Basically, if you have try to get your assignments in on time, because otherwise everything like stacks up at the end of the term, which isn't good for you. There's a study that they did at a university some years ago where they divided a class in half, and they give one half deadlines spread throughout the term, and the other half they just said all the assignments are due on the last day of class. And if people were good at like scheduling their time, the people who were told that you can submit everything on the last day of class should do better, but they didn't. They did worse. Okay, because people are not good at scheduling their time. They just kind of go, that I'm going to have a fantastic last 5 days. It's all good, right? So that's why we have deadlines. So officially, I'm going to take 5% off per day if you're late. If you have a good reason, send me an email. I can relax that, but try to hit those dates. I also realize it's a pandemic. It's been difficult, like last few years of university, so I'm going to tend to be kind of forgiving if you have a good reason. So if you're stuck on something, ask me, but still try to make the deadlines because you can get yourself into trouble if you fall behind on a bunch of them early on. Okay, so that said, I'm going to move on to why do we want to use FPGAs? And I'm going to try writing that on the board. So let's see. Okay, we'll try this and see what happens. And that looks promising. Okay, so the first question I want people to answer is why FPGAs? Okay, so we're going to talk about these kind of devices. You know, we should have some idea of why we're talking about them. What's the purpose? So, in particular, why not microprocessors, you know, for everything? Because that's kind of the most obvious alternative, right? Software is generally easier to design than hardware. So why don't I just program a microprocessor to do everything? If I could, I probably should do that. It's probably my most productive way to get things done. And often that is the right answer. So yeah, definitely that often is a good approach. But it's not always good enough. So there are kind of two fundamental reasons that FPGAs exist, in my opinion. So what do you think? Anybody have any idea why do FPGAs exist? Yeah, so one reason is performance. Okay, and there's a bunch of different ways you could define performance. So it could just be absolute throughput, you know, how fast can you get stuff done, or it could be performance per dollar, or often nowadays it's performance per watt. You know, or it could be some combination of those things. Okay, so why do FPGAs give better performance? So let's do that by an example. So first, they don't always give better performance. Okay, that's why partly we want to talk about programming models and different devices, because yeah, they're not always the right choice. But let's take an example computation. Okay, so take a simple quadratic equation. Can people in the back read this, by the way? Is this big enough? I mean, can people see it on, can you see it on the video or not? Oh, okay, so you're asking them if they can see it or not? Okay, maybe they've gone to their happy place. But okay, so we want to compute this quadratic equation. First thing we should do is algorithmically, I can actually simplify this a bit. Multiplications are more expensive than additions. So I can actually factor this to ax plus b times x plus c. And that's one multiplication, two multiplications, whereas this was three multiplications. A square, let me think. Is that three multiplications? One, two, yeah, three multiplications. Okay, so I've factored it. So I've rewritten it in a way where I'm going to need fewer multiplications. So that's just better. And let's look at how this would be done in a microprocessor. Okay, so which is kind of the default way you should probably think about doing these things. So in a microprocessor, we're going to break this down into a bunch of steps. Okay, so our instructions are going to sequence a data path and gradually build up our answer. So I'm going to make a really nice, simple microprocessor. So my microprocessor first has a register file. Okay, and in that register file, I can store a bunch of data. And let's see. So I can take a couple of operands out of the register file each cycle. Okay, I can put them into an ALU. Okay, so I can do addition, subtraction, or XOR, etc. And the output of the ALU can go back up and back into my register file. And let's say all these numbers are 32 bits. OK, so inside this register file, I've got a bunch of different storage locations. Let's say the first one I'm going to call temporary 1. OK? And let me write down all the storage locations that I'm going to need. So I'm going to need a couple temporaries. I'm going to need A. I'm going to need B, C, and my output Y. Whoops. OK. And I also have some control signals here. OK, so I have some control signals to choose, what addresses do I read from the register file, what addresses do I write from the register file, and what operations should the ALU do. And those control signals are going to be controlled by my program. The instructions are going to go through this one by one. So I can make a program that says, into location T1, put X. Into location T2, I want you to take A and multiply it by T1. OK, so I've got to read both A out on one of these operands, T1 out on the other, and set the ALU to a multiplication. And I'm going to send that back and store it in T2. OK, then I can say, let's take T2, and let's say it's equal to whatever's in there right now times B. And then I can update T2 again and say it's equal to T2 times T1. And T1 had X in it. OK, so I've done AX plus B. Whoops, that should be a plus. OK, AX plus B. AX plus B times X. So I'm almost done. I want to put in my location Y, that is my final answer, T2. And I have to add, well, what do I have to do to it? I have to add something to it. What's left? C, right? So I'm almost done. I just need to add C to it. OK, so this is my instruction stream. OK. OK, so this is the style of computation that you get when you write software. And it's in the context of FPGAs or hardware design, this is often called a temporal calculation. OK, so it's temporal because it occurs in time, right? I'm doing it in multiple steps. It took me 1, 2, 3, 4, 5 steps. And I reuse this hardware through those 5 steps to get my final answer. OK, so temporal calculations are fundamentally sequential. OK, so they're building things up in steps or in time. So it's easy to program, but that being sequential, you can see, could cause you some loss in performance. Where's my state? OK, maybe this is like such an easy question, you're just going to get confused. What do I mean? Well, where's my state in this problem? Yeah. Yeah, it's in the register file. And it's all in the register file. OK, so I have, we could call it a global state, or we could call it a centralized state. Because it's all in the register file. OK, so from a programming model point of view, that's actually quite nice. Like, all my data is just in one spot. I refer to it. Well, here I'm referring to it by name, but that can be turned by an assembler into just addresses. So it's pretty easy to refer to my various data. I can always get at all my data because it's all connected to my ALU. So it's a nice programming model. But this also can be a performance bottleneck to put all your state in one spot because it can be a bottleneck. This is a very simple processor. So you can build more advanced processors that are not, my processor is completely sequential. It does one instruction at a time. Modern processors are not so sequential. They overlap a bunch of instructions. So they aren't as sequential as this, but they're still not fully parallel, right? The instruction stream does break the computation into steps. They then spend a whole bunch of hardware trying to figure out which steps they can partially overlap, but they can't fully overlap it. And it takes them a lot of hardware to try to figure out which steps can overlap. Okay? So processors, can extract limited what's called instruction level parallelism. And in a classic kind of processor, like an Intel or AMD x86 processor, this is all done by the processor. So the programmer doesn't have to worry about it. It just figures out that I can partially overlap some of these instructions, which is great. Keeps the programming model simple for the end user, but it needs lots of hardware. Okay, so if you want to hide that and just extract it, you can only get so much parallelism, and it takes a lot of hardware. Okay, so let's compare that to, this is not really just FPGAs, but just let's build this in hardware. Okay, FPGAs are one way of building a computation in hardware. Maybe I'll start here. Okay, so in hardware, if I want to do the same quadratic equation, this is hardware. So you could say, well, that's a form of hardware, and it is. But this is kind of a specific form, processor-style hardware, temporal, sequenced hardware. Another kind of hardware that I could build is basically spatial hardware. I'm just going to actually build all the hardware I need and have data flow from one unit to another, and it's just going to directly do the computation. So I'm going to draw that out. So I've got this X coming in, and it's going to go to a multiplier. And I need to get X squared. That's part of what I need here. So I'm actually going to feed it into both inputs of this multiplier. I'm also going to take X, feed it into another multiplier, and the other input's going to be B. Okay, so now I've got X squared there, I've got BX here. Okay, I need BX plus C. Okay, so I could build an ALU. But I don't actually even need a full ALU. So an ALU has control signals to say, are you adding, are you subtracting, are you ANDing? So I'm going to actually build something simpler. I'm just going to build an adder. And I'm going to add C. Okay, the output of that is X squared. I'll build another multiplier, and I'll multiply that X squared by A. Okay, so I've got AX squared, I've got BX plus C. All I need to do now is basically add these two things together. Okay, so I'll build another adder. Again, I don't need an actual full ALU. I know I'm only adding, so I'll just build an adder. And the output of that is Y. Okay, so I've built, instead of building one ALU in a register file, I built 1, 2, 3 multipliers and 2 adders, and I wired them all together. Okay, so this is intrinsically parallel. It's fundamentally working on multiple things at once. It's also what we call a spatial computation. Okay, and it's spatial. I guess because I'm putting different operators down in space, I'm not just building one central compute unit, and also because my state is distributed in space. There's no one spot where all my state of my computation is. There's not a central register file where I've got everything. My state's basically distributed across the various wires in different spots. Okay, so it's got no central state. And in this kind of computation, I can also use specialized operators. Okay, so what do I mean by that? Well, in the processor, I built a general purpose ALU because I'm going to use it for many different things over time. Right? I've got control signals that are coming from the instruction to say what it should do. Here, I only need everything to do one thing, so I can specialize them. So for example, instead of ALUs, we're using adders, because we know we never have to do subtraction in this particular computation. And that's beneficial because specialized operators are smaller and they're faster. Okay, so I'm going to erase some of this. Okay, so do you think this is much, if I just send in one number, I send one x in, I get one y out, and I do the same thing here, right? Basically go through these 5 steps. I send an x into the register file, and I go through 5 steps, get a y out. What do you think? You think this is faster than that? They're the same speed? What do you think? Okay, so you think this one's faster. Do you think it's much faster or a little faster? What do you think? Okay, so it's probably somewhat faster, okay? But I do have to wait for yeah, it's going to be somewhat faster. So but I do have to wait for the computation to finish before I can send the next data input in with the way I've designed this. So I send in this x value. I need to multiply it once, multiply it again, add it. So the speed at which I can clock this is going to be limited by what is the delay of 2 multipliers plus the delay of 1 adder. Okay, and then I can clock it that fast, and I'll get an answer every clock cycle. Now this one I need to go through 5 clock cycles before I get an answer, because I have 5 instructions. The speed of those clock cycles is actually probably faster than the speed of that clock cycle, because I just need to go through one ALU. So that ALU is going to have a multiplier in it, it's going to have an adder, it's going to have some multiplexing. So it's going to have somewhat more delay than the multiplier. Okay, a multiplier is slower than an adder, so, but an ALU that can do multiplication and addition is going to be slower still because of the extra muxing. And there's going to be some extra delay to read things from the register file and to write things back to the register file. So this clock frequency is going to be, well, it's actually a little unclear, right? This clock frequency can probably actually be a bit faster than this clock frequency, but it's going to take me 5 cycles. So yeah, this is going to be faster. Which one do you think is bigger? What do you think? These are somewhat unanswerable questions too, because you don't have like an ASIC library in front of you and I haven't given you that much information. But what do you think? You think this one will be bigger? It's hard to say actually. So with 5 registers, it's not going to be too big. The ALU is going to be, it's going to be bigger than 1 adder or 1 multiplier, but maybe not as big as 3 multipliers plus 2 adders. So my guess, but this again is a guess, it's going to depend on how efficient the register file is and so on. This one's probably going to be smaller, okay, because of the fact that we're reusing our computation. We built one general purpose ALU and we use it for everything. That's what's making us slower because we need to go through 5 cycles, but it does also make us generally pretty area efficient, okay? So that's where we stand right now. let's see. Okay, so that's basically what I just said. Now, if I was going to do this computation once, this doesn't make a whole lot of sense, right? Because you don't want to build hardware. If you're going to just do a computation once, software is going to be fast enough. Don't worry about it. So what you care about more is when you are basically sending a stream of data in, okay? So let's see, I'm thinking what the best way to write this out is. I'll write it here. So let's say this is a stream. Okay, and what that means is, let's say we've got x of 0 and then x of 1 and dot, dot, dot. So every clock cycle we send a new x value in. And with this hardware, every clock cycle we could get a new piece of data out. Okay, so a y stream, so y of 0, 1, dot, dot, dot. Okay, so that is a more reasonable way to, that's a better motivating example of why I would build hardware like this. I got a whole bunch of data that I need to run through this quadratic equation. I may be doing some signal processing in a microphone, so I don't have just one piece of data. It's like every fraction of a millisecond, I've got another piece of data to deal with. Okay, so this will work. I can basically, if I send a new, so I put a register out here and a register out there, I can send a stream of data in and get a stream of data out. But I can optimize this. So what would you do to make this more efficient? So I could get more throughput out of this with a relatively small change. So what should I do to this hardware to make it more efficient? It's going to cost me a bit of area, but it's going to improve my throughput a lot. What do you think? So you just make more of them? Like just make, yeah, so I could make multiple units. If I made multiple units, I could get twice as much throughput at twice the area cost. So I could do that. I could replicate. But there's an optimization I can do in hardware that's an even better trade-off. Okay, I can basically spend less than twice the area and get more than twice the throughput. So what do you think? Yeah, so I should put registers in this. I'm limited in how fast I can send the new data in by what's called the critical path, right? So how long is it going to take me to go all the way from input to output?